So in this tutorial, we will go in depth on how to create a 2D drawing using Kuka PRC for drawing with the Kuka robot. The first thing we need to do is actually create a parametric geometry or any type of geometry to 2D draw. For our purposes, we'll start off with something simple and we'll use a point to give us our beginning parametric geometry. So I'm going to type in construct point, and I am going to give it an arbitrary slider value. I want my value to be at 50, and we can use this to begin our parametric drawing. We can give these all pretty much the same coordinate for our purposes, and from here we will go on to create a circle. Because what's simpler than creating a circle? Oh, so we need a circle component. That's our, where we need a plane and a radius. So our base plane is this point. We can give it the radius of 50. And from there, we now have a circle showing up in our Rhino workspace. From here, we can go on to create more circles. So we'll create this pattern where we have circles rotating or circles embedded in other circles. So what we need to do is actually create more points for these circles to go off of. So what I will do is divide this curve. I type in divide curve. Um, you need an initial curve to divide. We will divide this circle, and we will need an actual number of points to divide it by. So if we just copy this over our slider value, we can change this value to half of our radius. So if I change my numeric value to 25, gives us a nice working number for an even division. So for each point, we can go ahead and create a circle for it. So we can just copy this circle component over and give it a series of points, a radius of 50 like we had in the original one. I will copy this down, and now we have a cool looking circle inscribed in other circles. So this is kind of our base geometry. Because we have a whole list of circles, we need to actually flatten it so it reads better for our data. And from here we can kind of see that we have a series of 25 circles. Awesome. We will then take this geometry and shove it into another geometry component just to be safe. I want to flatten it again so I know it is working properly. And from here, we can group all this together and give it a nice group. So we know moving forward what all these components do. They create our parametric geometry. Take this, going to group it, parametric geometry. Awesome. Now, because we set our base plane not at our working plane or our calibrated plane, we need to project it to that plane or project it to a working surface that we can easily manipulate it to. So from here, we're going to project this geometry to the world plane. This is really helpful when you manually drew a 2D drawing in Rhino, but it also works for a parametric drawing, something that you've also done in Grasshopper. We want to be able to reuse this template for years to come, whether it's a Grasshopper driven geometry or a manual drafted geometry. So what we will do, we will type in our project component so we can actually project it. We are going to feed it our parametric geometry, and we also need to get a area point or a center point to actually orient it to the plane that we need, which is going to be our world XY Z plane or our world XY plane. So from here, we'll type in area. We'll feed our geometry into the area component. This gives us a area of each of our geometries and a list of center points. From here, we can take just the average of this. So if I type in average, the average center point, and we get something roughly in the center. And from here, we can then orient our geometry using that center point to the world XYZ plane. So we will feed it our geometry. We need an initial plane, which is our average center point, and we will also feed it the XYZ plane, XY plane. I'm sorry. So now that we have this all together, we have mapped our geometry to the base plane. Let's go ahead and turn off the preview for all of this. This is the one we're working with. We want to keep this one, but we will turn off all this. So let's turn off the preview, and now we can see that we have our geometry mapped to the XYZ plane, the same, or the 0, 0, 0 Rhino origin point, the same where we have our custom tool at. Okay, let's group this together and call it project to world origin. So now that we have our geometry mapped to the world origin, we want to be able to move it parametrically across the origin or in any direction. So what we need to do is set up a series of sliders that allows us to move our parametric geometry or our 2D geometry that we've inputted. So the first thing we need to do is create another point. So we'll go in and construct a point. And then we will also feed it a set of sliders. Let's do 500 to 0, well, negative 500 is less than 0, which is less than positive 500. So with that, we will duplicate it and feed it into this construct point. With this together, we can now create a 2-point move or a vector move. So if I do a regular, if I just copy this construct point component, I can disconnect the wires and automatically gives us a point at the world origin 0, 0, 0. So the next thing we want to do is create a vector 2-point to get a transformation vector. And we will plug in our world origin to our point we actually want to translate it to. So we can actually slide around and see where that, we can actually slide this and see where it moves to. But for now, let's just leave it at 0. So now we have this vector, we want to be able to move our oriented geometry based on the world origin, the world XY plane. So we will do a move command. We will move this vector into the transformation vector, and we will copy our geometry and move it to the geometry. Now if we look at, turn this off, now we can move our geometry parametrically across the origin, and we know that it's mapped correctly to the origin or our working plane because when we actually inputted our base calibration, it turned our calibrated base to the world XYZ plane or the world XY plane at 0, 0, 0. So now we know that we can map our geometry across our Rhino workspace. Let's move it a little bit closer to the robot. So I'm going to move a little further out. Say around 85. Then maybe 350 to bring it in front of it. And then let's raise it up about 110 millimeters. We're going to raise it up just to be safe when we actually run our toolpath. So for now, let's group all this together and call it parametric move. Awesome. So now we have our parametric move completed. We have projected our drawing to the world origin, and we actually have created our geometry. All right. The next thing we need to do is create the toolpathing, a series of toolpathing commands that will help us simulate our geometry. Okay, so the next thing we need to do is actually create our plane toolpathing. So the first thing we want to actually do is to divide our curves. Actually, not divide our curves, but actually create a series of points along our curves that we can then create planes from. So one thing that we can do is use a curve to polyline tool. So we type in 2 polyline. Just saw it. Curve to polyline. We can map our geometry, which is a series of curves, and then give it a tolerance to actually create polylines. So we just need a regular slider, regular number slider, and we can move it up. So we look at this, we can see it's all square and boxy. The more tolerance we add, smoother it can become. So move it all the way up to about 780, 770, wherever really looks correct. So from this polyline, we can actually get the control points from this polyline that we just created using the tolerance. So we type in control point. We can now create a series of points along those curves. It's a lot of control points. So the next thing we actually can do is use these points to create a series of planes. Now there are two ways to go about this. One, we can actually flip our plane geometry to map correctly to our tool, or we can actually just map our tool to the plane geometry. For now, we can use it. We can actually leave our tool as is. So if we go to our custom tool, we can take off 90-degree rotation, which we know is not needed at the moment, and leave it straight up at a positive 138 millimeters in the Z direction, and manipulate our planes to read so our tool and our planes line up. So what we would do if we were to do it using this method, we can create a XZ plane where we switch the X and the Z orientation and utilize a plane flip component. So what we will need to do is input a series of planes. So we would map our control points to this XZ plane and create a plane from the XY or XZ, and then map this XZ plane to the plane flip. This utilizes some booleans. So if I type in the boolean toggle, I can then determine which direction these planes will flip. Actually, let's turn off the preview. So now we can flip the plane. In order to flip it, we can utilize the plane flip component with false, change this to true, and then change this also to true. And now we have successfully switched our X and Z planes. So from here, let's group this all together, and we can call this plane toolpathing. All right, after completing some toolpathing, we can now create some drawing movements. So the first thing we need to do in order to create a drawing movement is to create a linear movement component. So we type in linear movement. We see that it takes in a series of planes and a speed. We will input our flip planes, and then we will also need to put in our speed. Speed typically is very slow, so 0.02. You can use it as a number slider, and we'll slide that into our linear command movements. So right now we have a series of movements from the robot to the drawing, but they're all connected. Each circle, if we were to do it using this linear move command, would be connected. So all those circles that the robot would draw would be connected, and there will be a line tracing from the end of the last circle drawn to the first point of the next circle to be drawn. So we can actually add a series of pickup movements using a Cartesian offset command. So what we can do is type in Cartesian offset. It takes in a series of commands, so these linear commands. It needs an X, Y, Z actual distance to actually pick up. For us, we will use around. I will put a slider in at 50 just so it's more visible, and we can use the same offset speed of 0.02 millimeters per second. So now we have a series of commands that we can feed into our core component. Oh, let's do this one too. And this pretty much makes up our drawing movement commands. We have a list of circles to draw with a series of pickup points to add in between each drawing. So we can just group this together and call it drawing movements. What we need to do is actually pull out the first plane the first plane over here in this list of planes, and then give it a copy and move that copy in a way that it's positioned right above our first point. So there are no extra rotations along any of the robot's joints. So in order to do that, we need to actually take out that item from that list of points. So what we would do is create a list item. We need to actually flatten our series of lists that we're going to put in. So we put this list in, we can flatten these lists, and we can just get out that first point. So index 0 is automatic, and we don't need to worry about wrapping. So in order to actually use this, we need to deconstruct it. We can just deconstruct vector to deconstruct this plane and get a series of XY values from it. These XY values can be mapped back into a construct vector. In between these, we can add a series of additions. So we can add actual numeric values to it to move the individual x, y, z coordinates. So I will also give it a slider. Typically, we can reuse one of these earlier sliders. So I copy this, and I can just move this all the way over here. Oh. And insert it right here. So now we're adding 25 to each point. So if I make another copy, we're going to do this for the x point, the y point, and the z point. Z goes to z, y goes to y, and x goes to x. So from here, we've just created the point. Let's see if I can see it. We may need to edit our sliders and make the max a lot higher. So what happens if we make it 100? Actually, we can leave these at 0. And then move this slider all the way up. So now that we got the vector for our actual movement of our first plane, we can kind of clean this up a little bit so it's a little bit easier to kind of work with later on. And now we can use a movement command in order to move our first plane. So if we do another move, we can take out that first list item and put a transformation vector on. And now we can see that we moved it up 100 millimeters. We can actually change this, our slider, so we have a little bit higher max. Okay, and now we can move it up as high, a little bit higher. I think about 250 is good. So from here, this is our new lead-in point. Let's group all this together so we know that this actually creates our point-to-point movement. Let me add movement at the end of that. Point-to-point movement. And then we can type in a point-to-point command to actually give us our first command for this maneuver. So point-to-point movements are slightly different than linear movements. They take their speed and velocity. Uh, their velocity is actually percentage instead of a meters per second. So for our percentage to do, just do 5%, and we'll add that to our velocity. So now we have our first point in our command, which is the first point we want to hit, then our series of drawing movements coming from this linear movement and our Cartesian offset movements. So in our KUKA core component, we first want to add our first movement, which is our point-to-point movement, followed by, it starts to see how the simulation is working it out, followed by our linear movement, our linear command movements. So right now it's giving us a whole bunch of lines. What we need to do is actually flatten this. Flatten, it just gives us one. Actually, let's go back. Instead of flattening our actual Cartesian offset movements, we need to flatten our input. So we just flatten this down here. Now shows our simulation working properly. Okay, so the next thing we want to do is actually select our tool mesh. We know that we have set our custom tool to the number 6 and that the height from the origin point 000 to the TCP, the tip of our custom tool, is 138. And because we are doing the plane manipulation method instead of the rotate 90 method, we do not need to add the rotate 90 across the B axis of our tool. We solve that through this procedure here using the plane manipulation. So the next thing we need to do in order to put our tool on our actual simulation robot is to set one mesh. And once it's set, we now see that we have our precise tool. See that it's added up here and that we are good to go. So from here we can actually run our simulation. So from here we can see that our simulation is actually running. It's stepping up in between every single point, and we can also zoom in to check and make sure that it's running properly. We can also hide all these planes, turn off the preview, and we can see that it's hitting each point individually and it's coming up correctly 50 millimeters after each circle. One way we can actually check our simulation is to also run this analysis tab from the actual KUKA PRC core component and hit play, and it will automatically create an animation which you can speed up and check. One thing I don't like that I see is that it's actually doing some sort of rotation on this way in. It's rotating to get to that first point. In order to fix that, we can bring this first point higher up. And we can actually add this point-to-point command into it because it's not actually mapping to it. So if I disconnect my Cartesian offset, plug this point-to-point movement in first and then hit shift, I can add multiple. If I hit shift, now it's coming straight down. And then we can check our simulation to see that there's no more, it's no longer rotating in order to get to that point. Just coming straight down like we want it to. Oh, one last thing we want to do in order before we actually export our source file for the robot, we want to move our actual drawing closer to the base. So one thing we can do, we can turn on the preview to see where everything lines up. I do a custom preview for our working cell. We can see that it's higher. So one thing we can do is add a, we can do an addition component and add another slider to it that moves our geometry lower. So we know exactly how much we're offsetting it by. So what you want to do is leave this at 0 first, and then as you run your source file, let me hide this. As you run your source file, you can see how far off it is and then adjust the height of your drawing as it gets closer to your paper and your base. This is also explained in the following video, actually running and executing. So you can leave these pretty much as is. You want to verify that your base number is actually matching the correct base number. Because our base is loaded, base is loaded in. Oh, it's not actually matching. Base should be 21, or frame number is 21. But because it doesn't go that high, it will actually map to the correct one. So on here, it shows you what custom tool number you have. We know it's 6, which is correct. We pretty much do not touch any of these start end positions. And using the analysis tab, we can actually do an animation of our actual toolpath. So what you want to do is actually set the project output to a location. If I want to save it to my documents folder, I can save it to my documents folder. If I want to save it to my desktop, I can save it to my desktop. But from here, you will want to actually add that source file to your USB drive and then use that USB drive and copy that source file to the robot. And that concludes setting up a 2D drawing in Grasshopper.